and welcome to this lecture on Introduction to Deep Learning System, which I will take it later to the part related to convolutional neural network and possibly another type of neural network with deep structure. This is an important component in the field of deep learning system, as we spoke about earlier. Assignment number 2, which is going to be posted today in the afternoon, is going to have a component, problem number 3, related to deep learning system, so that you train yourself on the material I will be sharing with you today and in the next week or two. Mahmoud is going to do a tutorial today at 8 p.m. I will email all of you about it. And I encourage you to attend the tutorial because it has some component that would be certainly beneficial for you to solve at least 2 of the problems of the assignment. There will be another office hour on Tuesday, and the students are welcome to attend it as well. And I encourage you to attend it because it's going to tackle the CKIT package, which could help you solving one of the problem of the assignments or other type of problems similar to it. I just wanted to mention that this assignment number 2 is at the fundamental of application of neural network. So this is the type of problem that you are going to encounter in the industry, whether for area of classification, whether for the area of clustering, or whether for the area of implementation of a neural network, whether shallow or deep. So this is an important assignment, and I would like you to spend time on it. I will give you 2 weeks, as I promised you last time, and I hope you are going to learn from it as much as possible. As we discussed before, so every a few slides, I will give you the opportunity to ask a question, and I will be happy to respond to those questions. Assignment number 2, number 1, by the way, solution have been posted as I emailed you last time. The marks will be posted for you, and if you have any issue or any questions about marking of a particular question, please feel free to email the TA about it. Okay, so let me go to my slides here. Okay, so these slides have been posted already on Learn. And this lecture will be, which is being recorded, is going also to be posted later on during the day on on Learn as well, in their recorded lectures for the course. So why deep learning? Why, I mean, this area, I mean, with a huge interest, why people are looking at it so with great interest? So we are going to tackle this particular component, I mean, in the early part of this introduction on deep learning, so that you are, I mean, it's not stupefied about the usage of these type of architecture. As we mentioned, deep learning is a particular component of machine learning systems, so it's only a smaller component in terms of the algorithms, but in terms of the usage now, it's becoming one of the most widely used area in the field of machine learning and even in the area of artificial intelligence. So we are going to see the secret why it is doing that, but we are going also to see what are the type of challenges that encounter designers when they are using deep learning, and whether should we use all the time deep learning or not all the time, depending on the type of problem. Deep learning might not be useful for small classification problem, which might require a perceptron or even an Adeline or Madeline system, but they become extremely important for other type of problems, such as pattern recognition, such as video tracking, object detection. So a number of applications we are going to see why deep learning is excelling on this particular type of application. So let me go here. So deep learning, so this is the generic learning process that we have seen in the past. So I took this image from Leo Rokak website. I have shared it with you, I believe, in the early description of machine learning system. So let me recall the various steps for having a generic learning process, whether it's connectionist or it's based on support vector machine or other type of naive-based classifier or other type of predictors. So first of all, you have the real world, you have the system that is surrounding you, and then you have the various type of sensors, whether they are cameras, they are sensors, they are wearables. So they are measuring devices, so they are extracting the information from the real world into signals. And then these type of signals are going to be pre-processed, so they are going to be filtered, and they are going to have certain type of representation, namely the feature extraction. So we are going to extract the best possible features out of these particular type of representation. The representation could be a speech signal, it could be an image, it could be a video clip. So it could be anything. And then we normalize it. And one of the problem in assignment number 2, which is on clustering system, is the normalization of the signals, how to normalize them for them to be all of them within a particular type of range, to calibrate them within a particular type of range, so that the range could be easily accessible by the machine with which you would like to do the classification or the clustering. So you will see that part in assignment number 2 that I'm going to post today. And then you have dimensionality reduction. Why dimensionality reduction? Because sometimes, as we spoke about it, in the area of unsupervised learning, the more dimension you have for a particular input of the system, the more complex that you have to deal with the problem. And that could lead to overfitting of the system if we design a connectionist model with small amount of data. So basically, if your input data has very high dimension, and if the number of inputs with which you are training the system is small enough, creating a complex structure for the machine learning system might not help you. So what we do, we usually do a dimensionality reduction, similar to what we have seen in the area of Cohen self-organizing map, and which you are going also to see in problem number 2 of the assignments, where we are reducing the dimension of an input or an image or a visual cue into from 3-dimension type of color to 2-dimension type of color system by utilizing the feature outputs of Cohen self-organizing map. One of your classmates has asked about another dimensionality reduction tool, namely principal component analysis, which provides the best type of components of the input that has most of the features. So sometimes you might have 10-15 dimension of a particular input, but mostly the 2 or 3 most important components that convey information about that particular input is only restricted into 3 inputs. So we would like to project that particular input signal into the 3 most relevant type of dimensions, so that you reduce the dimension of the system. If we have a little bit of time before I get to the part on fuzzy logic system, I will provide you with the presentation on principal component analysis, which is a major feature in the area of feature selection or feature projection. We are going to see today, actually, in the area of deep learning system, how important this dimensionality reduction and how the features that we are going to select are very, very important to help us with the learning and with the creation of a predictor type of model. And that is one of the major motivation behind utilizing this type of neural network known as deep neural networks or deep machine learning based system. So we are going to see that. So feature selection, feature projection, feature projection, especially for PCA, we reduce the number of features to the most relevant ones. We project them on the space for which they are the most relevant. And then we create our classifier or our clustering type of body or clustering type of model for the system. So the classifier, as we have seen, it could be machine learning based on a neural network, such as an MLP. multi-layer perceptron system. It could be a support vector machine that could provide you with the capability of separating between various type of classes, 2 or more classes. It could be clustering when we are dealing with unsupervised type of learning systems. So all of these are important components. So this, I mean, the classification categorization of the output. So the system has an input data, and then it has an output data at the outset. And then we create a model, and that model is going to be created as we have seen in assignment number 1, training the system, do n-fold cross-validation system in order for you to get the best possible type of system that is not going to overfit. And then we do the model testing to make sure that we have the best possible outcome, and then we are able to commercialize the system or to utilize it on a wider range of data sets that have not been seen by the system. So if we don't have a lot of underfitting, if we don't have a lot of overfitting, and if the test model provided us with the best possible type of outcome, so that's the particular model that we are going to do. And then we do analysis results, I mean, even further to make sure that that's the best model that we have. And if it is not, then we go back to the feature selection, we go back to the model, and then we do the model testing, and we do a loop of analysis over particular type of models. So that's what we have seen in the generic learning process. So why researchers keep developing new algorithms? Why the algorithms of 1960 or 1970, 1980, 1990s, or the 2000s are not always useful over a particular range of application? Simply because there is no best algorithm for all applications. Some algorithms are appropriate for certain type of application. So if you have a very simple type of system that is binary, where the data is linearly separable, why should you go to the most complex multi-layer perceptron and do the classification? You don't need to do that. A beautiful perceptron or a beautiful Adeline could help you with that particular system, and a lot of people utilize this type of things up to this day. So the perceptron that has been discovered in the 60s and early 70s, I mean, with the improvements, is being utilized nowadays in a number of companies. Some of them are large, some of them are small. So depending on the application. However, some of other applications, such as object detection, such as movement detection or movement labeling of a human or an animal, what are they doing? What are they, I mean, within a particular type of environments? Then we require most probably more complex type of systems that are going to provide us with the classification and with the understanding of what that particular gesture or that particular animal or that particular video clip means within the context of a particular operation. So this is what's happening. So there is no best algorithm for all application. However, the more complex the application becomes, the more the algorithm has to be sophisticated and suitable for that particular application. Nowadays, I mean, we have become acquainted with the streaming type of data. I mean, from whether stereo data, whether video data, whether speech data. And these type of data are certainly very interesting. But mining these type of data and making use of them for certain type of application becomes more and more complex when that data is not very clean, when that data is not labeled, when the data is very, very huge, not knowing whether an algorithm is scalable enough to deal with them or not. So in the past decades, advances in big data storage and processing power of machines and the algorithms such as the Hadoop, the MapReduce, have allowed people to explore more complex machine learning tools. And these type of big data storage and processing power of machines, if it were not there, then we are still stuck into major problems such as computer vision for nowadays, such as object detection for autonomous vehicles. So these type of problems wouldn't be solved, especially solved in real time, because nowadays we would like to deal with these type of challenges for having, the simplest example, an autonomous vehicle with the autopilot system of the level 4, which means that the car is completely autonomous. So the driver, or not the driver, the passenger of the car gives, 100% confidence into the car or the truck or the bus to take it from one location to a destination without any type of issues or without any type of problem, while avoiding traffic accidents and everything. So if it were not for these type of discoveries, which is, the advancement in big data storage, such as clouds, and processing power of machines and software such as the Hadoop, the MapReduce, and mega type of databases, the existence of mega databases, and of course, complex algorithms that are able to support and to mine this type of data, we wouldn't talk today about deep learning. Why I'm mentioning that? Simply because deep learning has been discovered as early as the 1990s. 1991, 1992, LeCun has published one of his early convolutional neural network. A number of people are not familiar with it, but convolutional neural network, have appeared in the early 90s. And Schmudeber and LeCun have developed algorithms separately to deal with this type of systems. They are we are going to see the structure of this convolutional neural network during today's lecture, but these type of systems have been developed. But I even heard from them, after my PhD degrees, I remember about deep learning, but not many people were interested in them at the time. Why? Because implementing such an algorithm, would be a nightmare on its own, even to solve very, very, very simple type of computer vision type of problem. People did not have the capability of big data storage. People did not have huge amount of computational power to deal with this particular system. And they require large amount of computational system. And if you would like to execute them in real time, it becomes almost impossibility at that time, because we did not have GPUs at that time. Even the CPUs in the early 90s were not very much developed. You have to solve this problem using supercomputers at the time to be able to solve some of these problems. So that's why the area hasn't prospered in that time. However, people in 2005, after 2005 to 2010, 2011, recognized that now we have big data storage. Now we have huge, powerful computationally powerful machines that are able to implement these deep learning systems. And that's when people such as Jeff Hinton, such as LeCun, and other researchers starting to work with these systems and to revive them. So I needed to give you this particular introduction to showcase you that these things have been existing for mostly 30 years now. It's almost 30 years since deep learning was there, but people did not use it. Only over the past decade that it has seen the major progress that we are seeing today. So some of the things that I just spoken about. So these are the history of the state of the art. We spoke about them in the early lectures, but I would like to remind you about some of the major milestones. So the first milestone is the perceptron by Rosenblatt, the AI winter, where Minsky and Papert have published their textbook that the perceptron is not able to solve non-linearly separable system. And then the area has been revived in the work of Rumelhart, Hinton, by developing the backpropagation learning algorithm that you are quite familiar with now, and that was in 1986. And then several type of directions for utilizing naive Bayes classifiers or support vector machines. That was 1990s, and up to this day, we are seeing these things. And then Hinton, LeCun, and others have revived the deep learning system because there is an importance in managing this type of learning system. And some of the major type of successes started to come in 2010, 2011, 2012, when people started beating benchmark type of data set and beating, I mean, performances that have been improved, I mean, very, very, very slowly. But in 2012, I mean, with the ImageNet and with the AlexNet type of network, they were able to solve benchmark problem while exceeding by almost 20% in terms of performance of recognition of other type of benchmark studies. And then literally after those type of studies, the area of deep learning has exploded, literally in terms of use and in terms of application in various type of areas. So this is historical type of background in this particular area. So yeah, this is, I mean, the perceptron that we have seen, that we have used in assignment 1, and you have seen some of the problem, the classifier type of problem. They are still being used, by the way. The multi-layer perceptron, which is a more sophisticated version to deal with multi-objects classification and to deal with the nonlinear separable type of system. But again, we have seen that the issues of linear separability, of the fact that we are only able to classify only one of two classes for the perceptron, have made the perceptron useless in complex type of operation. The multi-layer perceptron, which was able to solve the non-linearly separable type of data system and complex classification problems, have difficulties in terms of the training. And you have seen this very well on problem number 3 of the assignment number 1, when the system is overtraining, when the system is not structured well. You have to do a lot of testing, a lot of training for various type of model in order for you to be able to get to the best possible system. Why? Because this particular area here, I mean, I'm showing it, I mean, on extracting the best possible performance for the system is located here. So in order for the system to perform extremely well, you have to have the error of your system to be convergent within this particular area. However, if the system is overfitting, that particular error of the system might be located in here. So while we are looking at the global optima, we are stuck in local optima, which might exist here, which might exist in this particular region. And that's why we have overfitting. So the system is not generalizable. Why it's not generalizable? Because we don't have the global optima. So that's the generalization. You have to have the global optima or the global minima for the particular error. And this is extremely difficult when the system becomes quite complex, when the system becomes with thousands upon thousands of weights, which we would like to minimize or which we would like to optimize so that it responds to the larger, wider prediction type of problem where the variance is minimized and where the bias also is minimized for the model that we are creating at the end of the day. So we have major difficulties here with the overfitting of the data, with optimization and the difficulties of the training of the system, as we have seen in some of the problem. So these are some of the major issues that we have encountered with the MLP type of perceptron. So this type of multi-layer perceptron has a number of type of issues. So let me summarize them. So there are limitations. We call them shallow networks. So when we speak of multi-layer perceptron, where you have the input layer and then you have multi-layer systems that are processing the information from the input to generate the output, we call them shallow network. We call them shallow network even though the network might have 10 to 15 layers. We still call them shallow networks. We are going to see why. Shallow networks in terms not only of the processing of the information, but in terms of extracting the best possible type of features. The multi-layer perceptron do not have ability of extracting the best possible features of the inputs, and that makes them very, very difficult to utilize. So if you are going to recognize an image for a particular system, whether it's a cat or a dog or an elephant, you have to go pixel by pixel for the neural network. So the input of your system could be of dimension of, thousands upon thousands of inputs. The larger the number of inputs of your system, of course, the more difficult to deal with this type of inputs, and the more difficult to generate an excellent type of model. So the huge number of parameters, namely the weights between the parameters, especially when you are dealing with large inputs. So if you have a 10,000 inputs at the onset of the neural network, the multi-layer perceptron, and if you have, let's say, 20 layers that are connecting between the input to the output layers, you will end up with millions, literally millions of weights that you need to optimize. So that particular picture here that I showed you, which is here a 2-dimension, it's omega 1 and omega 2 weights, presuming that the MLP has only 2 dimensions, and this is the error. Imagine if these 2 dimensions will be expanded to multi-million dimensions, because we are going to have multi-million weights that we have to optimize, and that error becomes a function of many millions of weights. Imagine the horror of that particular problem that you would like to solve. So that's why the area of a neural network did not see a lot of improvements in the 90s and even in the early 2000s, because it's almost impossible to realize in real time a neural network with multi-thousands of inputs, which is the case for images or even for video clips, because video clips, it's a sequence of images. So imagine that particular difficulty. Of course, because of this huge number of parameters and the large area of the large dimensionality and the huge size of the network, we are going to for sure overfit, because our system is not going to be studied, very, very easily. Remember problem number 3 of assignment number 1, even though it's 1-to-1 dimension, and you saw how many type of difficulties you encountered by optimizing these type of weights for that one particular type of layer. Imagine if you are dealing with, instead of 10 weights or 200 weights, such as problem number 3, you are dealing with millions, literally millions of weights. Imagine how we are going to do. So that leads to no generalization, which is the big problem in the area of machine learning systems. So this is one major problem, and of course this leads to many local minima, because that particular picture that I showed you in the early part, instead of having 2 dimensions, now imagine that you are going to have, so this is the error, you are going to end up with millions of dimensions, and how are you going to control the local optima of the system? So this is a highly non-convex structure of the error surface, and this is a very complex problem in the field of mathematics when you are dealing with highly non-convex structure characterized by high non-linearity. So back propagation algorithms becomes ineffective due to vanishing gradient through the layers. So we did not mention this, we mentioned it, I think, in a minor way, but when you are dealing with a huge number of parameters, when you are dealing with large number of layers, when the system back propagate from the output layer to the early set of layers, we are going to have very, very small values of the weights. When the values of the weights become very, very small, they generate very small values of the gradients. So you are doing minimization of a gradient between layer 10 and layer 15, let's layer 11, between layer, actually, the 10 and layer 9, because we are back propagating, and the gradient is almost equal to 0. So how are you going to do that? So going from large gradients at the outermost layer to the layers that are in the input layer of the system, and you are going to encounter major difficulties. This is known as the vanishing gradient throughout the layer. Why? Simply because this system with huge structure is going to lead naturally to this particular problem. And that's why neural network haven't been successful in the 90s and the early 2000s, before 2010, before the advancements in deep learning, simply because of these problems. Why? Because now we are dealing with images of high definition that requires possibly tens of thousands of input in terms of the pixel. But at the same time, we are confronted with a huge structure of a neural network for which we are not able to optimize in real time. So this is no good deal and there is no solution for this particular problem. So people have said that we need to deal with other type of neural network structure that have better structure, better capabilities, and better algorithm to deal with this particular problem. So I wanted to give you an introduction here of the history and why people have started to migrate from shallow network to deep network systems because of these major problems. Because problems nowadays are becoming quite complex and we need to solve them in real time. Solving a problem, I mean a neural network, running it, training it with a new type of data in real time, it's almost an impossibility. So that's why we require new type of architecture, and this type of architecture are going to be, I mean, we are going to look at them, we are going to see some of them, but I'm going to focus most naturally to the convolutional neural network, which is the convolutional neural network, convolutional neural network system, which are becoming conventional neural network in the field of deep architecture systems. So that's what we are going to see. So I will stop here and I will take one question or two if you have any, and I will be happy to listen to you, or you can feel free to write them here. So I will wait for a few seconds, and if you have some question, I will be happy to respond to you. Okay, so far no questions, good. So let's proceed now to talk about the deep learning architecture. So what we are going to see here, so I'm not going to go deeper into what is required for the machine learning system. There are a number of deep architectures, deep learning architecture systems. So there are the deep belief network, there are the stacked autoencoder systems, there are convolutional neural network systems. There are other type of restricted Boltzmann machine, RBM. So there are a number of them that are being utilized. I'm not going to go over many of them, but I will give you, I mean, an overview of what is happening, and then I will jump to the convolutional neural network system that we are going to talk about. So I will give you some of these architecture in order for some of you who are going to work in a particular area, when they hear about deep belief network, they understand what it is. When they hear about stacked autoencoders, they know what it is. Convolutional neural network is another type of deep neural network. So these are for static based neural network. There are known dynamic deep architecture systems that are utilizing other type of architectures, namely the deep recurrent neural network, long short-term memory type based deep type of neural network, which we are not going to tackle in this course. They are I mean, another whole area of deep learning systems. And when do we use them? We use them for dynamic systems, such as time series type of dynamic models, systems that are changing at every instant of time. Images that are changing into video clips. I mean, we could utilize the recurrent neural network for video clip systems. So I'm not going to touch on those ones. I would like to give you a good firm foundation, at least for some of the deep learning architecture, and then I will enumerate for you major type of neural network. And if any one of you has some interest in knowing more about the deep learning type of architecture system for dynamic system, I will be happy to share with you that material. And then we are going to see the application in vision, speech, and natural language understanding. Natural language understanding also use version of recurrent neural network. And then we will talk about the advanced topics in optimization as related to the implementation of these particular type of system. So let's look at the difference between standard processing machine learning and deep learning system. Again, I took this picture from the website of Kevin Du here. I like this picture. It's very, I mean, transparent, and it provides you with an excellent way for understanding things, okay? So let's look at the standard process in machine learning. So that's the early one, the early slide that I shared with you today. So you have the raw data that have been extracted by sensory system, and then you have the hand-engineered features. So hand-engineered features, we can do principal component analysis to to make sure that the dimensionality of the input of the system is only relevant to 2 or 3 or 4 type of dimension systems. But most of these type of tools, we call them hand-engineered features. You have to go through a meticulous type of process to select these type of features to present them to the model. Once we have these type of hand-engineered features, so that's not an automatic process. It could be, so the hand-engineered features could be pixels choice, or it could be certain type of features within the image in the form of 3 or 4 type of dimension within a particular representation space of that particular image or that particular signal. Once we have these type of features, then these type of features, or what we call them attributes, are going to be utilized as input to a particular neural network. So these are the features, and these are our, it could be neural network, it could be support vector machine, it could be anything. So these are the connected type of layers here, and then you have the outputs of the system here. Okay, so you have the input, which has been reduced through the hand engineering features, and here you have the output, which is going to select for you an image that has a cat, that has a dog, that has an elephant, or it's going to detect for you a sound of a particular type of importance within certain type of environments. So this is how it works now. I mean, for the shallow network system, even though it might have a large number of layers within the neural network system. So this is the standard process in machine learning, and we have been using it since before 2010, I mean, for almost every type of application. And the decision here means the classifier, I mean, outputs or the predictor type of information or a map if your input signal is a continuous one, similar to what we have seen in the in problem number 3 of assignment number 1. So I would like to relate this type of development, this type of algorithms to what we are seeing in the assignment. Because when I give you these type of assignments, I meant this type of problem. I meant to provide you this type of problem. I know that they might be a little bit of challenge. They might be, I mean, for those of you who are not familiar with machine learning, they might take you a little bit of time, but at the end, it's worth the effort, because that's how you are going to learn machine learning system and how you are going to understand the insights beyond this type of representation. So assignment 1 has been one. Assignment 2 is going also to showcase you a number of things that you require to learn when we are dealing with this particular type of problem. So this is the original system. Now we are going to come to the deep learning. What are the major difference? The major difference is these red type of components. What are trainable features? That's the secret. What are trainable features? Trainable features, they are simply, take it here, at least at this particular stage, they are autonomously extracted features. So we are developing here a structure of the neural network, a layer of the neural network that is automatically extract the most relevant features of the system. Instead of hand engineering them by utilizing various type of tools, I mean, some of them might be successful for that particular application, some might be not. We are going to automate that process within the particular area of the network. So the network now, instead of receiving these type of elements here that have been pre-hand engineered, we are going to create another structure here before it that are going to do the processing. So this is the red area here. And these here are going to be the raw data. So this could be the images. This could be anything. This could be the video clips. But here we are going to have these special layers. So I call it special layer, which is going to help you with the trainable feature. Once these trainable features have been extracted, then we are going to utilize the neural network that we are accustomed with, which could be an MLP. Okay, so this could be an MLP, but this is the part that is the fundamental of what we call deep learning system. So this is where the deep learning component occur. And I'm going to explain to you later on under CNN, or convolutional neural network. So the deep learning component is mostly this particular area, which is going to provide us with the trainable feature. So whenever you hear deep learning, remember that it's the layer before the trainable feature that is going to provide us with the trainable feature coming from the raw data. That's what the deep layer. So here we don't have deep layer. See, here we have a neural network similar to here. Even if you have 10 layers, 15 layers, it's still not deep. This is what gives the problem the deep layer, because this deep layer indeed has several types of structure. We are going to see them, especially when we are going to look at the convolutional neural network type of system. So that's what I wanted to share with you in this very, very nice and very insightful type of picture that I took from the website of Kevin Du here, to illustrate the deep learning type of system. Okay, so let me explain to here what are these type of deep layers. Okay, so why we call them layers. So a family of methods that use deep architecture to learn high-level feature representation through kernels or energy function, followed by supervised structure for tuning. So in this particular case, this is going to be the deep learning components of the neural network. So what the deep learning components is going to do? The deep learning components is going to utilize set of filters. This set of features is going also to convey this particular type of information. It's going to coalesce them. It's going to put them together so that they are going to make sense out of further type of shapes that are of importance to the object that you are training with. For this particular example here, we would like to detect people. We would like to recognize humans within a particular type of picture. So we are going to train the system with all these type of people that are living in that particular building, for instance. And when that person comes to that particular visual type of system or computer vision type of system, the system is going to detect you, recognize you according to certain type of features. These features have been extracted a priori before by training on tens of thousands of human faces. But later on, once we have that particular training models of these type of layer 1, layer 2, layer 3, now we know that the deep learning component is able to extract layer by layer the various facial type of features for human being. Once we train it with the people that are living in that particular type of building, then the system is going to recognize them every time they show up at the door of the building or at the door of the office or any other type of places. So this is what we call the deep learning type of components. And these type of systems, we don't teach them, to do this. Simply, they are filters that are applied to the original pictures, and they are going to extract layers by layer. So layer 1 is going to be combined later on to provide the layer 2. So these are edges, and these could be filters of various type of aspects of the feature space. So what the system is going to do here is going to extract the features that are of most importance to a face. They are going to do it through several type of features. So some filters could be for a horizontal edge. Some features could be for a curved type of edge. Some feature could be for a little black, circle. Some feature could be for a vertical edge. So we provide these type of layers, these type of filters to the system so that they are able to reconstruct after a certain type of processing some of the more understandable type of features. So as you can see here, it's a face feature. And these happen just before we go to the layer of the trainable classifier. So what we are doing here, we are creating trainable features for the system. So I will speak about that a little bit more in details when we are going to tackle the convolutional neural network. So this is the deep learning system in a nutshell, and we are utilizing here especially the representation in the form of convolutional type of feature for the system. So what are convolutional neural network? Which is the most used type of deep architecture. I mean, as I mentioned to you, LeCun has especially, I mean, 1989, he provided an article, but it was in 1992 that he first published some of his early results on recognizing some type of visual type of features for certain type of application. So this is good fellow. I mean, he has published a textbook with a number of his colleague and former supervisor. And he mentioned that convolutional neural networks are simply neural networks that use convolution in place of general matrix multiplication in at least one of their layers. So what it means that suppose this is the original neural network, so that's the artificial neural network system. So there are two components for this artificial neural network. So there is the part which we call deep, and in this particular case for convolutional neural network, it says that if we use at least one particular convolutional set of filters, we call it, even if it is only one set of filters, we call it convolutional neural network. So it is a deep learning in itself because it's going to provide us with these type of features, the output features that are going to go to the usual type of neural network systems that we have seen, which could be very well be multi-layer perceptron. However, this multi-layer perceptron is going to have very, very well selected type of features. Instead of having hundreds of thousands of input pixels, is going to have possibly 500 or 1,000 of representative type of features, And then we can create a beautiful multi-layer perceptron that is going to be our good classifier for this particular model. So the work that is going to be done is going to be in this particular layer, which is going to be pre-multi-layer perceptron system. Okay, so we are going to see the convolutional neural network, more in depth later on. But the convolution operation pertains basically to utilizing, an original image, which could be composed of one layer, or it could be composed of multi representation, of RGB type of input system. So it could be composed of multi type of set of input here, RGB, for a particular image, and then the values could be, black and white, in this particular case, black and white. And then we do a certain type of filter, and then the filter is going to do a certain type of convolution, and this is going to be the convol feature. The convol feature itself could go through other type of convolution to provide you a more convol feature. And the main goal here is to lower the dimension of the original type of image, but at the same time, we would like to keep as much as possible the original type of information. So if we look at here, so this is the CNN learn filter on its own during training process. Look at this word, what it says, learn filters on its own. So this is an autonomous or automatic way for doing it. So we don't tell the system that you have certain type of gray area in this particular location and more somber area of the image. The system is going to go portion by portion, and is going to extract these type of features, whether they are edges, whether they are, salient feature of the image of the model, and it's going to do it automatically. And here you are going to have what is known as matrix multiplication or matrix convolution of a picture of an image with a particular type of filter to give you these particular images. So this is how the deep architecture of the system works, in the simplest type of representation. So this is how it works. This is the system. So this is the image, the complex layer terminology, and this is the simple layer terminology. So you have the input to the layer, two layers. So this could be the image. You do a convolution of the system. So this is an affine transformation. And then you are doing the detection stage, which is basically the nonlinearity. And then the system is going to utilize special type of activation function, the rectified linear unit, which we are going to speak about it later on. And then the system is going to utilize what is known as the pooling stage. This is known as the convolutional layer. We can have up to 10 or even hundreds of such layers if the input to the layer is extremely large. So I will showcase you, how these type of things work for a particular set of structures. So you have wide range of convolutional neural networks nowadays, characterized by the convolution stage, characterized by the nonlinearity activation function of the system, by the pooling function, and by the number of layers for the system. So here, to make it a little bit simpler, so you have the input to the layers, you have the convolution layer system, you have the rectified linear unit, the pooling layer, and then to the next layer. This is our two equivalent system, but here, this is one convolutional layer one. Okay, so then here you have convolutional layer 2. You repeat the exact same information here as you have done it here through several type of other layers. For those of you who have seen a convolutional neural network, this might be easy for you to understand, but I'm especially mentioning it for those of you who have never seen convolutional layer or deep learning type of representation of a neural network system. This is an example here that we are representing. So you have the image here, okay, and then you have the first layer output volume here. So this is convolutional layer 1, okay, so it has a certain type of depth here and a certain type of width, and these type of width corresponds to the number of filters that we are using at this particular level of the system utilizing for this particular image. And most of the time, this type of width represents not only the filters, but also it represents the how many channels of this particular image. Because when we are dealing with RGB channels, you might end up with 3 type of inputs blocks like this one. Each one of them represents the red, the green, and the blue type of nature of the color picture. So we will talk a little bit about this one later on when I give you more details about the convolutional neural network. And then you have a second layer output volume. So this second layer output volume is characterized by more type of operations rather than by the width of it. Okay, so each block here has a depth, width, and the height characterized by the filters and by their characteristics. Once we arrive at this particular level, so here we are going to end up with very output numbers here. These particular numbers are going now, each one of them is going to take an input of these dense neural network system, which is going to be the fully connected layer. So this is what we call the fully connected layer, where we are going to connect every element of the outcome of this particular layer to the large number of inputs, which we have learned for our classifier for the multi-layer perceptron. And this fully connected layer system now is going to do the classification problem. So the classification problem is going to occur here. So why we call it deep learning again? Because of this. This is going to provide us these type of features that are optimized and that are automatically extracted from these type of deep learning architecture. That's where deep learning comes from. It comes from this particular area, which is generating for us the best possible feature, the automatically extracted feature. This is not hand-worked type of features. These are automatic features. So deep learning, remember it, it's given for these particular structures. And we have seen here the green and the yellow, but we might end up with tens of layers to give us later on the fully connected layer of the system. Problem 3 of assignment 2 is going to showcase you how to write these type of networks, how to implement these type of networks. So I wanted to showcase you there how to implement for the first time, for those of you who have never seen a CNN system, how to implement a CNN using certain type of libraries. And I suggest all of you attending or looking at these lectures today to attend today's tutorial, because Mahmoud is going to speak about some aspects of these type of implementation, because assignment number 3 that I am going to put forward today at 4 p.m. is going to include that particular part. Okay, so this is going what I wanted to share with you. So this is a little bit more detailed picture of what we have, and as you can see, the early part here, the first filter, I mean, is going to cause this particular system. So this could be one filter, this could be a second filter for this system, and this could be this particular components of the system. And later on, all of them are going to be features that are going to represent for this particular neural network system. Okay. So this is what I wanted to share with you in this slide. So if we go to the details, as I mentioned to you here, so these we have nose detected, eye detected, edge detected, similar to this particular level here. So this is the early set of filters here, and then these type of things are going to be merged together to create the face. So this is the face. The leg also could be part of other type of features, and these features could be part of some other type of features that are known as others. So the leg will be another components, and then you are going to have fully connected system that is going to have the face and the leg and the other ones that are going, each one of them is going to go to a certain part here, and then this fully connected layer is going to generate for you later on human body system that is detected. So that's how it works. I mean, this is very, very representative type of things on how this type of system works. Okay, so this is the convolutional neural network. I will go quickly on deep neural network, which we are not going to see in this course, but mostly this is very important because it's related to dynamical systems. Look at the dynamical system here. So where basically the instant at this particular instant of time, it depends on the instant, I mean, on the previous type of information that has been gathered by that particular system. So these are going to be states. I mean, each one of them is going to be sequence of states, which we are going to accumulate together to represent a particular behavior of a system. So it's a sequence of information that are going to be concatenated with each other to represent a particular signal. That's what a recurrent neural network does. Okay, so for instance, we speak a word. I mean, cat, for instance. We know that cat, we wouldn't understand cat if we don't utter syllabus of C-A-T in a particular type of sequence. So if we respect the position of each one of the syllables of a cat, then we should be able to understand the cat. Okay, so when we are doing a signal recognizer of particular words, then we are going to train the system to recognize a sequence of elements that represent themselves an entity. Okay, so this is known as recurrent neural network because, I mean, now we speak a cat, then we speak a dog, and the succession of these type of elements, the dynamical behavior for recognizing a particular word gives it the dynamic type of representation, and this is what we know as recurrent neural network. So a lot of problems related to the area of natural language understanding deal with this type of deep architecture known as recurrent neural network systems. So in general, when we are doing, I mean, a deep learning system, so we would like to map, I mean, an input to an output type of component. We have several type of hidden layers that go, I mean, from the input level to the output level. So in the area of the convolutional neural networks, these type of hidden features are the ones that are made through the convolution. Okay, so certain other type of network, they do not use convolution, they use other type of approaches. So for instance, for the deep belief network, for the stacked autoencoder, they use other type of layers. But these layers ultimately are going to have a certain impact on the mapping between the inputs and the outputs. So let's look at this particular system for the deep belief network. So for the deep belief network, which we are not going also to look at it, so it's a certain set of machines, we call them restricted Boltzmann machine, which are going to represent the understanding of what that picture means, what that signal means in terms of an energy-based model that we are going to represent for that particular system. So each one of these type of hidden nodes is going to encapsulate a certain level of energy that is coming from this particular type of input set. And these type of input sets, and these are the hidden type of variables, are going later on to convey the information to a later type of hidden layers that are going to convey ultimately the information in the bigger way. So I'm not going to go over the details on this deep belief network here, which is the restricted Boltzmann machine, but I would like only to mention to you that there is an interaction between these type of input system and these type of hidden layers, as you can see, and these type of interaction are characterized by these type of energy level type of representation between the input and the hidden layer type of system. Okay, we can go not only one layer, but we can also create several type of layers. So here we call it layer 1 RBM, layer 2 RBM, layer 3 RBM. So this is similar to what we are seeing in the field of convolutional neural network. I mean, these type of extractor of the information, so here we do it in the form of energy level, are the same as we are seeing in the area of convolutional neural network. So these, what they constitute, what is known as deep belief network or radial basis restricted Boltzmann type of machine. They are also deep neural network because of the autonomous level by which we extract information hidden in these inputs within this particular type of information. So this is again completely different from the multi-layer network, where we have activation function. They do a certain type of filtering, and these do not mean a lot in terms of the output feature that we are going to extract for the system. So these systems here are going to filter out energy or signals or whatever into a certain set of more sophisticated, higher level of information. This higher level of information, ultimately, it's going to be the output feature, which is going to provide the features that are going to go to the fully connected neural network, which is an MLP type of neural network system. So stacked autoencoders. What are stacked autoencoders? Similar to what we saw, I mean, in the previous two slides. We have the input of the signals, and then we have hidden layers of the system that are going to encapsulate this particular information. And then here we have an output of the system that is similar in nature to the input. Why we are doing that? Why we do this? So simply we do this in order for us to restrict this type of hidden layer to make it more representative of the input to the output. So if the input here, and this is the output of the system, what type of mapping is going to restrict from three type of, three type of nodes into two type of nodes. So these two type of nodes are encapsulating all the information that is hidden into the system. This is a little bit similar to what we have seen for the coherent self-organizing map. This is going to be done, in a supervised manner, so that we are reducing the dimension from 3 to 2 and then to 3. So this here, what the system does here, if we are able to train the system and train the model, so here we are going to compress this particular information into this information. We are going to send this information through cables or whatever in order to make it less expensive on us and to utilize less bandwidth. And then once we reach our destination, the system is going to decompress it through this particular learning between H1 and X'1. Okay, so this is an encoder which encodes the information from X to H, and this is the decoder which is going to decode from H to X'. Okay, so we call them autoencoders. They are excellent type of tools that are going to compress the information and then decompress it in order for us to utilize it. They are utilized, I mean, in a lot of cases to reduce the noise of information, even for small channels, but they can be used, I mean, for many type of other applications. And these type of systems are also very utilized. Stacked autoencoders or autoencoders, they are major components on deep learning systems, because here these type of filters that we are creating, I mean, these type of H1 and H2 type of filters are no other than filters that are going to help us out to extract that information between the input to an ultimate output of the system. And as you can see here, there is a difference between this type of system and the multi-layer perceptron. So stacked encoder, so we would like to minimize, of course, I mean, the information between what we generated and what we have in the middle type of layer. So I'm not going to go also on the details for the system, but we could use for this particular model the backpropagation learning algorithm for this particular system, where we have this type of system. This is the input, and this is also could be utilized as the input of the system, because we know this input and we know the output of the model, and we would like to extract these type of encoder that will compress the information and then release it later on to have the same type of information. So this are the autoencoders. So there can be also several layers of the encoders, and that's why we call them also deep. So this particular area here is the deep learning components of the system, which generates, I mean, this particular type of outcome. So these have been utilized in a lot of communication and even in a lot of computer vision type of model systems. It is used as well, as I mentioned to you, in the case of noise, for taking the noise of the system. So what we can do here, after we train a system without noise, then when the signal is corrupted with noise, utilizing the H1, H2 that have been able to extract the information or the energy from this particular input, and then this particular system now is going to generate for us as less noisy feature as possible, because they have been trained early on something that is not noisy. So when you are injecting the noise, the H1 and H2 in this particular system are going to recognize the effect of this type of noise, and they are going to provide you with the clean signal. So this is also one other use of the autoencoder type of system. Why deep architectures work in general? So deep neural network can feed the training data in many ways by optimizing lower layers as much as possible before optimizing upper layers. So the lower layers here are the one that are providing the deep learning system its name. So we would like to optimize them. We would like to create all these type of filters before we send them to the fully connected machine learning classifier, which is at the end of the deep learning type of structure. Even if lower layer are random weights, upper layer may still turn well for this particular system because of the robustness of the system that we are trying to train. Pre-training learns more generalizable features. So similar to that example that I showed you for the features, I mean, so we can take a neural network, and this is very important information for you, which is known as knowledge transfer, or knowledge transfer between various type of neural network. So let's suppose that you have a merchant or a seller of information, and he tells you, excuse me, 1 second, please. He tells you that I can sell you a neural network which has all these type of convolutional type of features. I have trained it over hundreds of thousands of faces, hundreds of thousands of human bodies. Okay? And then you say that because these are very expensive things to do. So this is what we call the pre-training of the system to provide, I mean, an early version of the model which you are going to train. So these things are very expensive to do because, I mean, getting pictures, training the system on offline type of structure. So what you say, yeah, I'm going to buy it from you. Why? Because I can do the knowledge transfer over my network. So what you do, you utilize, let me go back to the picture here, the insightful picture that I showed you a few moments ago. So you are going to buy this part that requires a lot of money, I mean, for particular, I mean, or a lot of resources, money, not money, but a lot of computational resources. And people are willing to do it. So they tell you that I have trained for human detection people, I have trained hundreds of thousands of people at different type of posture. And if you would like now to adapt your network to a certain type of population living in a building or living in a manufacturing cell or in a manufacturing factory or whatever, then you can utilize what people have created here. You don't need to do it again. And then you are going to input your own images. So this is the knowledge transfer between neural networks that have been created and others. And what the system does, so this is the most difficult component here. And this is what your system is going to classify for you. So this is, you buy this one or you take it offline, you have your own image, and then the system is going to be trained to provide the best possible weights for this particular neural network, which could be an MLP, fully connected MLP type of system. The same thing for recognition of digit recognition. So you can have a company that developed an excellent recognition system for digits. So you buy that one and then you apply it for your employees who write in a certain type of way. And then the system becomes perfect. Not perfectly, but very, very well adapted to the write-up of your people. And then they can generate out of their write-up possibly some text, which you can use later on to archive it or document it. So this is the knowledge transfer of the information that we utilize it in deep learning system. So I'm going to stop here today, and I'm going to see if you have any type of question before I start, talking about the CNN type of neural network. As I mentioned to you early on in the lecture, applications are almost infinite nowadays for deep learning system, from computer vision, object detection, image classification, behavior recognition, scene understanding, to speech recognition, speech translation, natural language understanding. Remember, these will be done through recurrent neural network, which we are not looking now. Decision support system for navigation models, or for banking application, for healthcare applications. The applications almost are endless. As long as you are able to structure your problem into signal input and signal output in terms of decision, in terms of classification, then utilizing deep neural network systems is becoming, the way to go and the way to utilize. And I'm happy to tell you that, in assignment number 2, we have a full, problem, which is number 3. So I don't advise you to work on it immediately until possibly after I finish the lecture on Monday, where you can start, grasping the various type of important items. But I suggest to you to start looking at it and to attend today's lecture, today's tutorial by Mahmoud in the afternoon. I expect that every one of you have received the link to connect you to Mahmoud's tutorial today at 8 p.m. If not, please email me, because I send it through the Teams. I will stop here and I will take some questions from you if you have. If you don't have any questions, then I will be happy to respond to you as well offline by email, or send my TAs if you need any type of information. Okay, so I'll give you minutes, and if you have questions or anything, I will be happy to respond to them. If not, I will let you go, and we meet again on Monday. Okay, I'll stop here then, and thank you again for attending, and have a good weekend, and I'll see you then on Monday. Good day.